Welcome to our quantum deep dive. Today we're digging into something truly mind-bending, an idea from an essay by Jörg Owe Schneepat. We're talking about an atom made of both matter and antimatter.
Yeah, it's a particle that feels like it shouldn't exist, something that just defies common sense. But it holds the key to some of the biggest questions in physics. It's called positronium.
I know what you're thinking. That sounds like something straight out of science fiction, right? You take a particle of regular matter, an electron, and you pair it with its perfect opposite, an antiparticle called a positron. But this isn't fiction. Nope. It is a real, though, incredibly fleeting system that physicists are actually creating in labs to test the very fabric of reality itself. All right, so here's what we've got lined up. We're going to break down what this exotic atom actually is. Then we'll see how it stacks up against its more stable cousin. We'll look at its fleeting existence, find out what it's actually used for, which is super cool, and finally, touch on the huge quantum future it represents. So, first things first, before we dive into all its wild and crazy behavior, let's just get a really clear definition of what we're actually talking about here. Okay, so forget every atom you learned about in chemistry class. Unlike all of those, positronium has no heavy nucleus at its center. Nothing. It's what they call a purely leptonic atom, which really just means it's two incredibly lightweight particles, one from our world of matter and one from the world of antimatter, stuck together in this kind of delicate dance, all held together by the electromagnetic force. You know, to really wrap your head around just how strange positronium is, the best way is to put it side by side with the simplest atom we all know and love, hydrogen. Think of positronium as hydrogen's really unstable cousin. On the surface, they might look a little alike, but man, when you dig in, the differences are just massive. And this chart just lays it all out so clearly. Let's look at the core. A hydrogen atom has this big, heavy proton. We're talking over 1,800 times heavier than its little electron. Positronium, no core at all. The electron and positron are equal partners, which changes everything. Look at the binding energy. It's exactly half of hydrogen's. But the real kicker, the most dramatic difference, is right there at the bottom. Lifespan. Hydrogen is stable. It sticks around. Positronium, on the other hand, is basically born to self-destruct in a tiny, tiny fraction of a second. And yeah, that self-destruct button is really the most important part of its story. Its entire existence is, well, it's just unimaginably brief. It's born from a chance encounter, and then, poof, moments later, it's gone in a flash of pure energy. And we're not just talking about decay here, like in a normal radioactive atom. This is total, complete annihilation. Just look at that number, 125 picoseconds. To put that in perspective, in the time it takes light to travel less than 2 inches, it's already gone. It just vanishes. And this all happens through annihilation. It's the ultimate showdown when matter meets its antimatter twin. So here's how it goes down. It's a perfect demonstration of Einstein's famous E=mc². A positron, which is just an electron's positively charged twin, gets drawn to an electron nearby. For a split second, they form this exotic positronium atom, and then they collide and just vanish. Their entire mass gets converted into a burst of high-energy light, these gamma-ray photons that shoot off in opposite directions. So it's not really destruction, it's a total transformation. Mass becomes pure energy. And here's where it gets even cooler. It turns out not all positronium atoms are the same. How it dies actually depends on a quantum property called spin. So if the electron and positron are spinning in opposite directions, it's called parapositronium. That one annihilates super fast into 2 gamma photons. But if their spins are aligned, pointing in the same direction, it's called orthopositronium. And weirdly, the rules of quantum mechanics say this state can't decay into just 2 photons. It has to take a slower route and decay into 3. This tiny little difference in spin makes orthopositronium live over 1,000 times longer. Now, that's still just 140 nanoseconds, but in the quantum world, that's practically an eternity. Okay, so at this point, you're probably wondering, why? Why go through all this trouble to study something that literally disappears in an instant? And the answer is actually pretty fascinating. It's because its depth is so precise and predictable that it becomes this incredibly powerful tool. Right, its short life makes it this amazing little probe. So scientists can, for example, inject positrons into a material, say a piece of silicon for a computer chip. Inside, those positrons find electrons and form positronium atoms. Now, here's the clever part. If that new atom happens to find a tiny nanoscale hole or a defect in the material, it can actually live a little bit longer before it annihilates. So by measuring that lifetime super precisely, scientists can map out the material's microscopic structure. It's kind of like sending in a tiny spy that reports back with a flash of light. And this isn't just for materials. The same basic idea is used in medical PET scans, where positron annihilation helps doctors see what's happening deep inside the human body. And then there's the really fundamental stuff. Positronium is basically a perfect laboratory for stress testing one of our best theories ever, quantum electrodynamics, or QED. That's our theory for how light and matter interact. Because positronium is so simple, just an electron and a positron with no messy nuclear forces getting in the way, physicists can calculate its properties with unbelievable precision. Then they can check if their calculations match what they see in experiments. It's also perfect for testing some really deep universal rules, like something called CPT symmetry. That's the idea that the laws of physics should stay the same even if you flip a particle's charge, look at it in a mirror, and run time backwards. So these applications are already pretty amazing, right? But the future of positronium research, well, that's where things get even more profound. It might just help us answer one of the simplest, but also one of the biggest unanswered questions in all of physics. We all just assume that antimatter falls down, right? That it reacts to gravity just like regular matter. I mean, all of our theories predict it should. But here's the thing. No one has ever been able to directly test it. The problem is that charged antiparticles get pushed and pulled around by any tiny stray electric field, which messes up the experiment. But positronium, it's electrically neutral. So if we can create a cold beam of these atoms and just watch how they travel in Earth's gravity, we could finally see for ourselves. Does antimatter fall down, or could it, against all expectations, actually fall up? So when you put it all together, this exotic, unstable atom, this fleeting dance between matter and antimatter, is actually a surprisingly powerful key. It's helping us unlock everything from the future of material science to the fundamental nature of gravity itself.
It really is a fascinating field of study, and we have to give a huge thank you to Georg O. Schneppet for the incredibly detailed source material that made this whole explainer possible.
If you want to go even deeper on this topic, you can find the original essay and a lot more at schneppet.de.
Thanks so much for joining us.